Welcome to the 11th lecture. We are studying stochastic processes and we'll continue studying Poisson process, and today we'll model the kth arrival time in a Poisson process. Before this, we have studied different items, including the parameter of a Poisson process lambda, and we have studied about the inter-arrival time, which is modeled using exponential distribution. The kth arrival time means that in a given time, suppose t, we are required to find out the probability that the kth arrival happens at time t. This means that just before time t we have k minus 1 arrivals. Since these times are overlapping and we cannot have t minus 1 time, therefore we write it probability that the kth arrival happens at time t as p y sub k of t. In conjunction with this probability, we define another probability, that is the probability of this event, the kth arrival at time t, times a small time delta. A delta is a very small time which is assumed to be approaching equal to 0, and this product is assumed to be a probability, the probability of kth arrival happening between this time. This means k minus 1 arrivals have happened before, and in this time we assume one arrival to happen, so that in time 0 to t we have exactly k arrivals, and the kth arrival is exactly at time t, right? So this can also be written as a product of two independent events, because having k minus 1 arrivals from 0 to t and exactly one arrival between time t and t plus delta, these two events are independent of each other. So we can write as this event as event A and this event as event B. So the probability of event A, that exactly k minus 1 arrivals in time t, which can be modeled using Poisson process. The Poisson PMF can be written as lambda times t to the k minus 1 times e to the minus lambda t over the factorial of k minus 1. And this second event, that exactly one event happens in this very small interval of time, is the probability of success. This can also be assumed as a Bernoulli process, where we are computing the probability of having one success in a small interval of time. The probability of success would be lambda times, this is lambda times t, but here this small interval t is lambda, so we'll write it as lambda times t. So the total probability of the two events, the joint probability of the two events, we have written it as a product of the probabilities of two events, because they are independent. So we can multiply them together in the second line, and when we multiply lambda times t to the k minus 1 e to the minus lambda t over k minus 1 factorials times lambda t. So this lambda makes it lambda to the k instead of k minus 1, where t remains to the k minus 1, right, times lambda. So this is the probability that exactly k minus 1 arrivals happen in this duration 0 to t and 1 arrival in t. This can be assumed equal to the probability that we have kth arrival between this small time t and t plus delta. So equating these two equations, equating equation 1 and 2, we get the probability of having kth arrival exactly at time t. Delta times yk to the t, y sub k of t is lambda to the k t to the k minus 1 e to the minus lambda t over k minus 1 factorial times delta. This delta cancels with this delta and we get this PDF lambda to the k minus 1 e to the minus lambda t over k minus 1 factorial. This expression is a PDF and we call it Erlang PDF. Which tells us the probability of having kth arrival at exactly tth time, at exactly at time t. This Erlang PDF can also be written as, suppose we have different, there is another way we can assume this distribution and we can find its mean and variance. Suppose at time t1 we have the first arrival, at time t2 we have the third, and at time tk we have the kth arrival in a Poisson process. Yk, a random variable, is assumed and it is equal to the time at which tk is the time at which kth arrival happens. If we know that from 0 until the first arrival happens, the time can be represented as capital T1. The time between first and second arrival is T2, this is T3, and if it is k minus 1 arrival, this time is Tk. So the inter arrivals, in terms of how can we write this Tk in terms of inter arrival times? Surely it can be written as, this Tk can be written as the time between no arrival to the first arrival, the time between first arrival and second arrival, the time between first and third arrival, and then between k minus 1 and kth arrival. So this time, which is the time at which kth arrival happens, is written in terms of inter-arrival times. These are inter-arrival time. This is the time at which kth arrival happens. This is the difference. This capital T represents inter-arrival time. So how can we find the expected value of this random variable? We know that all these times, inter-arrival times, are random variables, and we have already studied that for inter-arrival time we use exponential distribution. So each of these variables, t1, t2 up to tk, are random variable. Each of this is a random variable belonging to an exponential distribution. So we can find expected value of tk by computing expected value on all these random variables, and we know that inter-arrival times are independent of each other. We have already studied that in a Poisson process. Any two intervals of time, what happens, whatever happens in an interval is independent of whatever has happened before. So this is expected value of t1, expected value of t2, expected value of tk. And we know that expected value of t1, since the same process having the same parameter lambda, the expected value of t1 would be 1 over lambda plus 1 over lambda, since lambda is the process parameter, 1 over lambda. So this comes out to be k over lambda. So expected value of the inter-arrival time, sorry, this is the expected value that kth arrival happens exactly at time t is k over lambda. The distribution that governs this is Erlang distribution. So for Erlang distribution, the expected value is k over lambda. As the last thing for today, let's find out the variance of this fact that kth arrival happens exactly at time t. This is the variance of this small t, variance of t1 plus t2 plus tk, which can be, since they are independent of each other, this can be written as variance of t1 plus variance of t2 plus variance of tk. This means this is variance, each of these variables t1, t2, t3, they are exponential variables, and we know that for an exponential variable having parameter lambda, the variance is 1 over lambda squared, 1 over lambda squared plus lambda squared. So the variance of having of this Erlang distribution of having kth arrival exactly at time t is 1 over, this is k over lambda squared. So in the upcoming lectures, we will be moving to some other problems that will solve for Poisson process, and will start Markov process in our upcoming lectures. Thank you.